Okay, we're back with the second half of section 4.4, starting with the second fundamental theorem of calculus, which states if we're taking the derivative of an integral, it makes sense that they would kind of cancel out, but it has to be very specific where the bottom of the interval is a constant and the top is x. That will turn into f of x. So the x gets substituted into f of t, but the derivative and the integral essentially cancel themselves out. So here's an example of that. We're taking the derivative of an integral from 0 to x of the square root of t squared plus 1 dt. The second fundamental theorem says all we do is plug that x into the t. So the answer to this question is the square root of x squared plus 1. There is an extension to the second fundamental theorem, and that is if there's something up on top here that's anything other than just x, we have to do the chain rule for derivatives. Makes sense. So we're going to plug this in for t, but we're also going to multiply by the derivative of x cubed as well. Okay, so with constants on the bottom, so that's good to go. So we're going to plug in x cubed, but we're also going to have to multiply this by using the chain rule, multiply by 3x squared. So this is still considered the second fundamental theorem of calculus, and remember we have to multiply by the derivative of that top if it's anything other than x. So in this case we did have to do that. Okay, so now we're talking about rates of change. There's a lot of applications with integrals in terms of rates of change and um, displacement, distance, things like that. So for net change, if we have f prime is the rate of change of a quantity f, then the definite integral of f prime gives you total or net change. So doing the the first fundamental theorem of calculus, where you take the antiderivative, plug the top number in, plug the bottom number in, as long as we're talking about rates, this is just going to give you net change. So in a question like this, a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is the time in minutes from 0 to 60. Find the amount of chemical that flows into the tank during the first 20 minutes. So since we're given a function that represents a rate, if I take the integral of the rate, it's going to get me back to a total. Okay, so it's not going to be a rate anymore. I'm undoing the rate. So from 0 to 20 of 180 plus 3t dt, do the fundamental theorem. So take the antiderivative, 180t plus 3t squared over 2 from 0 to 20. Plug in 20. I'm going to get 4,200. My label, find the amount of chemical. So this is going to be in liters. Okay, so that was just reinstating that if we undo a rate, we're going to get back to a total. Okay, let's look at another application here, what displacement means versus total distance. So this is going to be in terms of velocity, position, things like that. So here we have velocity. From A to B. Okay, so we have three different sections kind of going on here. We have this section A1 that's above the x-axis. That would give us a positive number. We would have A2, which is underneath the x-axis, which would give us a negative number. And we have A3, which again is positive. So for displacement, I would subtract this little area because it's below the x-axis, but add the two positive ones. However, for total distance traveled, I would add all three of those pieces together because even though this is in the other direction, if we're talking about velocity, underneath the x-axis would be referring to going the other direction. I would still add that because I'm still traveling versus displacement where if I'm just saying how far have I traveled from A to B, since I walked backwards, that would not be counted for displacement, but it would be counted for total distance. So total distance, we're thinking about absolute value, where we would still add that piece on, but displacement, we would not. We would just be subtracting that lower piece. Okay, so let's look at the difference here in a couple problems. We have a velocity equation again, so we're going from velocity to take the integral of that would to undo velocity would take us back to position, which is how we're talking about a total distance traveled or a net distance traveled. So here we have velocity of a particle moving along a line. What is a displacement of the particle on the time interval from 1 to 5? So displacement means I don't, I do have to just take the integral of it. I don't have to worry about doing absolute value. It's going to cancel out those negative pieces on its own. So from 1 to 5, VT is going to give me my answer. So VT is t cubed minus 10t squared plus 29t minus 20. Antiderivative, t to the fourth over 4 minus 10t to the third over 3 plus 29t squared over 2 minus 20t. Evaluating that whole thing from 1 to 5. So we would be plugging in 5 first into everything and then subtracting the 1 getting plugged into everything. It's going to give me 32 thirds. So since we're moving along a line, this means this is 32 thirds units to the right of where we started. What is the total distance traveled by the particle on the time interval from 1 to 5? So in this case, I should graph it because I need to see where it changes direction, if it goes under the x-axis at all. Okay, so I'm going to use x, which is fine. X to the third minus 10x squared plus 29x minus 20. Okay, so I'm going to zoom in so I can see this little area a little bit better. Let's go from 0 to 6 and negative 5 to 5 instead. Looks like I should have gone a little taller. Okay, so here's 1. That's where our interval starts. And here's 5. This is where our interval stops. So I have to know what this piece is in the middle, where it hits the x-axis in the middle, to figure out how my interval is being separated. So I'm going to do second trace 0. I have a suspicion that that is happening at 5 or at 4, but I can't say for sure, so we need to test it. And I always just go right to the 0 functionality because if it's a decimal, I'm not going to see it on the table. This one is not a decimal, it's 4. So since we have to do the absolute value when we're talking about total distance, so we're going to have from 1 to 4, we're going to subtract off, oops, let's label correctly here, subtract off the integral from 4 to 5. Okay, so from 1 to 4, I'm going to do my regular function. And then subtract off the integral from 4 to 5 of the original function. All right, so now we're going to take our antiderivative. It's the same twice, so as long as you get it right the first time, you can just copy it back down. We already did it on part A. And this first function is going to be evaluated from 1 to 4, and then we're going to subtract off. Same thing. from 4 to 5. Again, I'm not going to show all the work for that. First, we're going to plug in the 4 to everything, then we're going to plug the 1 into everything, find what that value is, and then plug in the 5 and plug in the 4. So the first half, when I evaluate the integral from 1 to 4, I get 45 fourths. And then the second half, I get negative 7 twelfths. So we subtract off that negative piece so it gets added on. I get 71 sixths, and we're talking about feet. All right, so that is the entire section of 4.4. That was the second half about the fundamental theorem of calculus.